Hello, 2020 Inform's annual meeting virtual attendees. So happy you've joined our session. Today we're talking about IoT sensor reduction through optimal sensor placement. Rajesh and I are here from Kavi Global, a boutique data science consulting services, software, and solutions company based in Chicago, Illinois. Happy to introduce Rajesh, our R&D leader and one of the founders at Kavi Global, who will be my co-presenter today. Rajesh has over 2 decades of experience in data and analytics, AI, and breakthrough IoT solutions. Prior to his role at Kavi Global, he has led award-winning teams at GE. Rajesh also has 2 patents to his name in creating innovative no-code data engineering and data science platforms. I'm Naomi. I'm the head of Kavi Labs, where we partner with enterprises for various AI and IoT prototypes across industry. And prior to this role, I was also leading analytics teams at GE to deliver breakthrough IoT solutions for connected CT and MRI machines. We have seen a boom in IoT, or the industrial Internet of Things, and the rise of connected devices along with it. In our solution today, we'll see how IoT corrosion sensors can help tackle monitoring pipeline corrosion. Thanks to IoT capabilities, corrosion monitoring technology has significantly developed over the past few years. Software-based real-time corrosion monitoring is possible now because of remote monitoring and the frequent data points available connected to our assets and streaming the data in real time. This helps provide actionable insights on this real-time data. And this is what's led to this wide-scale adoption of corrosion monitoring solutions, especially in industries like oil and gas, refineries, chemical plants. And this makes sense because they have thousands of miles of pipelines that they need to monitor the corrosion rates of, see what is the thickness, how is it changing over time across the pipes. And corrosion monitoring is, of course, critical because we're hoping to detect any early warning signs of corrosion to avoid unplanned downtime, an outage, or an accident. So corrosion rates are identified by an electrical resistance to a thin film on a corrosion wafer. And this is really vital for knowing how to predict a critical moment in an application's lifetime. So in the current state of monitoring and placing sensors across these pipelines, they're placed uniformly or equally spaced across regular intervals along the pipeline, with this big assumption that corrosion rates are constant everywhere. But this is, of course, not true. This is a faulty assumption of the current state. So there are 2 key problems here with this faulty assumption and uniform placement. So since corrosion rates in fact do vary across locations, placing them uniformly can lead to unnecessary redundancy. And this drives up the cost of instrumentation of the sensors, the cost of data collection, processing. And in our solution, you'll see how we were able to reduce the cost by 1/3 by removing that unnecessary redundancy and saving on the sensor cost. Alternatively, another downside to uniform placement could be if there's a bend in the pipeline or the flow dynamics vary, it could be very possible that the uniform placement standards lead to some gap in coverage. So how can analytics provide value here? Well, by analyzing the time series historical data at each point in the pipeline from each sensor in the current state, you can deduce where there is some redundancy, right? If you were to monitor the sensors and see two that are physically close together and see that the rates are the same over time, you could say that the value coming from those sensors are correlated. And once you know which sensors are correlated or which ones are moving together, we can then make some recommendation about which ones might be unnecessary, which ones can we remove without compromising the quality of the data that's coming in from those sensors, meaning we're not missing out on any key area in the pipe. And we're also not over monitoring. So with that, I will turn it over to Rajesh, who will take us through the solutions, starting with the input data for this model. Rajesh, over to you.
Thanks, Naomi. So let's talk about the sensor reduction solution. And let's start with what did we get to begin with, right? So in the input, we have 16 sites and we have 40,000 plus assets. That means miles and miles of pipelines. We have 2.2 million sensor measurements placed in different frequency of distance at different locations and assets. And we have 30 plus years of historical data, right? So some of the data have been manually measured, probably closer to the 30-year range. And then later on, they have made some of the sensors smarter. So we have more frequent data collections. So we have data with different years with different frequency of measurement locations. So what we got is, we got the sites, we got the assets, we got the sensors, we got their position in next to each other, right? So we cannot group sensors which are not adjacent to each other into the same group. So that is not part of the requirement. So we got the sensors, their placement locations, and their historical readings for 30 years. And we are expected to analyze and find out what sensors are redundant. So if we have independent data points, right, if adjacency is not a problem, we have many solutions like clustering and stuff like that to figure out what is similar. Since we have to take into account their relative position to each other, what we did is we looked at their historical characteristics, right? The measurement mean, standard deviation, the correlation between sensors, to come up with groups, right? So if the sensors are adjacent to each other and they are highly correlated, right? So that means you could probably get away with one of the sensors, right? So now what we are trying to do is use various statistical measures to come up with proper groups. And once we arrive at the groups, we need to come which sensors should represent the group, right? So probably we can reduce a group with 10 to 2 sensors, right? Or we can reduce 3 with 1 sensor, right? And then we have a sensitivity analysis. So here we have various gears, right? So you can get really aggressive, or you can get really conservative in terms of reduction of sensors. So we also built in a module to do the sensitivity analysis. Let's say you have a group of 5 and you have to replace it with 3, then what happens? Right, this we do by looking into account the measurement distribution and the mean and stuff like that. So we also built in a sensitivity analysis which exactly predicts what would you miss if you remove excess sensors, or what is that you're not gaining if you have more sensors, right? So we built both the grouping algorithm, the recommendation of which sensor to be picked, and also a sensitivity analysis on what happens if you remove the sensor. So that's the algorithm we built. So for this we used inbuilt software called Plexa, which is a layer over Apache Spark in this case. So as I said, this was 30-year data. So we had to do a lot of data profiling to understand the data. They were in different formats. So we had to clean it up, make them standardized, implement various business rules to do the data harmonization. And then we had to create the grouping algorithm based on statistical and other AI methodology available. And once we did the recommended groups, right? So we need some user to go in and see the impact of it using the sensitivity analysis. And then we add a workflow to make them either allow or override the recommended group on the sensor placement. So this was a total solution built with Plexa with Apache Spark on the background. So what did we get? Like if you look at the readings, right? So these have been the a sample of the reading. If you look at it, we recommended 4 groups here. If you look at on the left, if the system is recommending, hey, these 4 almost look similar, right? And the 2, it kind of, I think, stretched a bit. And then 3 is separate, and then 4 is separate. So now this is based on a certain grouping ratio on certain parameters. Now the user can go and override, hey, the 2 seems pretty long. We might have to probably split this into 2, and we have built an application to do that. And then we also have the sensitive analysis on what happens if you split right after 8th point, then the next one become 3, or we can split that and going forward, right? So it takes into account all the characteristics of the data collected in the last 30 years to kind of simulate what would you miss or what would you gain if you go one way or another, right? So this is the tool, and somebody makes so the system makes a recommendation, somebody gives a manual touch to it, and somebody approves it, and they reduce the sensor based on that, right? So this is the solution we took almost a year to build, and this was very well received, and a lot of business people went through it and actually validated, hey, yes, they are redundant, they shouldn't be here. Now, if you see even within the same group, if the distribution is very high, then you can even add sensors, right? If you see the breadth is very much, the variation is too much, you can also add groups within add more sensors to the group as well. The system recommended these points, and it's reviewed by various engineers, both in the central location as well as on the field. We were able to reduce the sensors to less than 60% of the value with a 40% reduction of the sensors. So what they were trying to do is they were trying to upgrade the sensors. So when they were trying to replace, they don't have to replace one-to-one sensors. They need to replace only 60% of it, right? So that was a big saving. I think it saved a lot on the purchase price of the sensors itself. And it also reduces around 15 to 20 million annual savings at some of the sites because they need to, fewer sensors means fewer maintenance in terms of maintaining the sensors, lesser data points, lesser compute resources, lesser network resources, and so on, right? And we also recommended that at some places you might need more than the frequency which was decided, right? So we also were able to find certain assets where the variation was too high, even between 2 assets, in which case they had to add extra sensors to the location, which kind of proved really valuable to them.
Just a little bit about us. We are Kavi Global, a pure play data and analytics consulting company. And we've been delivering solutions to cross-industry clients. I look forward to all your questions and working with each of you in the future. So look forward to seeing each of you in the Q&A session. Thanks, and talk soon.